All right, so we want to find a basis for row space, column space, and null space. So first of all, we want to notice that our pivots are here. And so the row space is going to be the space that is made up of the rows that contain pivots. So it's going to be those 3 rows. We can either use the rows from the row reduced version, or we can use the rows from the original. So either of those are going to give us the same space. So we can say that the row space of A is equal to the span of these vectors. So I'm just going to use the row reduced version. And then the column space is made up of the columns from the original matrix. So this one, it actually does matter because row reducing actually changes the column space. So it will be the, so we have these columns have pivots. So it's going to be the space made up of the columns corresponding to the columns that have pivots. So those 3 columns. So the column space is going to be the span of these vectors that make up the columns. Okay, and then the null space of A, we're going to find by thinking about this row reduced echelon form, and we want to find the, so we take the matrix, we row reduce it, which is, we already have the row reduced form of it. Okay, and so we have our pivots are here, here, and here. And so that means that we will have a free variable here and here in the columns that don't have pivots. We'll call that S and T. And so we are going to have that x1 is equal to negative 2s, x2 is equal to s, x3 is equal to 0 actually. So x3 equals 0 from this line. And then x4 is equal to t, and x5 is going to be equal to 0 actually. So the null space of A is going to be the span of the vectors, and we can just use these coefficient vectors from the S and the T. So it's going to be -2, 1, 0, 0, 0, and then we'll have 0, 0, 0, 1, 0. So there's our null space. Okay, and then I want you to, just to remind you how these spaces are related to one another. So in section 5.3 where it talks about which things are, oh no, 5.3 is Graham-Schmidt, so it's in 5.2 I think, where it talks about, theorem 510, where it says that the row space of, the row space of A, that the perpendicular space perpendicular to that is equal to the null space of A. And so the row space and null space are perpendicular to one another. And then we have that the column space of A that is perpendicular to the null space of A transpose. Okay, and so that's from theorem 5.10. So this is something to remember in case you're asked about finding a space that's perpendicular to another space, and if it's related to the row space and column space, then we know how to find those perpendicular spaces. Okay, let S denote the set of vectors x, y, z in R3 such that x times y times z equals 0 is S a subspace. And so let's go back to the definition of subspace. So to be a subspace, it needs to be closed under vector addition and scalar multiplication. Okay, so if you have the set xyz such that xyz equals 0, then I want to take like some, maybe we take like 2 of these guys. So if we have x times y times z equals 0, okay, so let's just think of an example. So that would be, well, anything that contains 0. So 1, 2, 0. So that is an example where x times y times z equals 0. If I add that to another one, say I add it to 0, 1, 2. That is another vector that's in that space. So these are both vectors in the space. That vector is in the space where x times y times z equals 0. This vector is also in the space where x times y times z equals 0. If I add those together, I get 1, 3, 2, and this is no longer in the space. And this is x times y times z is not equal to 0. So it is not closed under vector addition. So you can just pick 2 vectors in the space and add them. And note that I picked them a little bit strategically because I was thinking if the 0 is in a different place, then it should add up to something that doesn't have a 0 as one of the entries. And so that's going to give us something that doesn't work. Okay, so the next one, what does it mean for vectors to be linearly independent? What that means is that if C1V1 plus C2V2 plus ... plus CKVK equals 0, then it must be the case that C1 equals C2 equals C3 equals CK equals 0. So all of those coefficients have to be 0. So in other words, the only way I can add these guys up, a linear combination of these, and get the 0 vector is if those constants are all 0. So let V1 through V4 be vectors in R3. Is it possible for this collection to be linearly independent? And so the answer is no. Why? Because we have too many vectors. So we have too many vectors. We have 4 vectors in a 3-dimensional space. So V1, V2, and V3 could form a basis. Could span R3, but V4 would be in the span. Okay, so you can't span a 3-dimensional space with, well, you can span it with a 3-dimensional space with 4 vectors, but you have too many vectors. Okay, consider the chemical reaction, and there's a chemical reaction. Find a solution which balances the chemical equation. Okay, so we want to do like, so we'll just call these like X, Y, Z, W. So we could say X of those, Y of those, Z of those, W of those. Okay, so so we don't know how many of each of these guys there are. So now I want to just make some equations. So we have, what is C? Is C carbon? So for carbon, we can make an equation. So we have 3 carbon in that C3H8 plus, 3 carbon equals Z times 1. So, so on the left-hand side, we have X of those C3H8s, so that'll be X times 3 carbons, and on the right-hand side, we'll have Z times 1 carbons. And then if we look at the next one, hydrogen, we'll have X times 8 hydrogens on the left-hand side, and then we'll have W times 2 on the right-hand side. And then for oxygen, we'll have Y times 2 on the right-hand side, and on the left-hand side, we'll have Z times 2 plus W times 1. And so then that just creates a system of equations, and then we can solve that system of equations. so I'm not going to solve it. All right, so next we have a transition matrix for a Markov chain with two states. Compute the state vectors x1 and x2. So we just are going to do p x naught will be x1. So we'll do 0.4, 0.2, 0.6, 0.8 times 0.5, 0.5. Okay, and I'm going to plug this into my calculator. Do I have a calculator? Here we go. Okay, so I'll do 0.4 times 0.5 plus 0.2 times 0.5, and that gives me 0.3 in the top, and then 0.6 times 0.5 plus 0.8 times 0.5, that gives me 0.7. Not surprising, those guys should add up to 1. Okay, and then x2 will be px1. 0.4, 0.2, 0.6, 0.8 times 0.3, 0.7. And that gives me 0.4 times 0.3 plus 0.2 times 0.7. Gives us 0.26. And then we should get 0.74 for the other one. So let's do it. 0.6 times 0.3 plus 0.8 times 0.7 gives us 0.74. Yep. Okay. Find a steady state vector for the Markov chain. So what we want to do is we want to have that p times some x is equal to that vector x. Okay, so we want a steady state vector. And so we just need to solve for it. So the p is going to be 0.4, 0.2, 0.6, 0.8 times x, we'll just call it x1, x2, equals x1, x2. So we can write some equations there. So we have 0.4 x1 plus 0.2 x1 equals x1, x2, yeah. And then I'll have 0.6 x1 plus 0.8 x2 equals x2. So we can subtract it over. I get negative 0.6 x1 plus 0.2 x2 equals 0, and 0.6 x1 minus 0.2 x2 equals 0. And so I can see that that is going to reduce down to negative 0.6, and then 0.2, 0, 0. Okay, and so I can see that this is my pivot, which means I have a free variable here. I'll let that be t. So I have negative 0.6 x1 is equal to negative 0.2 t, and x2 is equal to t. And so I get, if I divide that over, negative 0.2 divided by negative 0.6, I get 1/3. So I get x1 is equal to 1/3 t, and x2 equals t. Now I want these guys to add to 1, so I can find the t by going 1/3 t plus t equals 1, and so then I can solve for t. So I get 4/3 t equals 1, so I can divide or multiply by 3 and divide by 4, so t is equal to 3/4. So I get x1 is equal to 1/3 times 3/4, so it's going to be 1/4, and x2 is going to be 3/4. So there's our steady state vector is 1/4, 3/4. Okay, now I have a linear transformation with those eigenvalues and those eigenvectors. What is TA of 0, 3? So, yeah, you can write 0, 3 as a linear combination of the eigenvectors. So just notice that 0, 3 is equal to 1, 2 plus minus 1, 1. Okay, and so I can say that TA of 0, 3 is going to be equal to TA of 1, 2 plus TA of minus 1, 1, which will be, there we go, which will be, when I do 1, 2, I know 1, 2 has eigenvector 2. So it's going to be 2 times 1, 2 plus, and when I do minus 1, 1 has eigenvector 3, So 3 times minus 1, 1. And so I add that up, and I'm going to get 2, 4 plus minus 3, 3. So that gives us 2 minus 3 is minus 1, 7. Calculate the matrix A. Okay, so the matrix A is going to be made up of, what happens to the, what happens to E1 and E2 under this transformation. So this is saying I can write the vector 1, 0, and 0, 1 as a linear combination of the eigenvectors. So let's see. So 1, 0 is going to be equal to, okay, it's not as easy to see just off the top of my head, so I'll just write out with, so it'll be A times 1, 2 plus B times minus 1, 1. So I just need to figure out what that is. So I have, so let's see, so what do I have here? So I have 1 equals A minus B, and I have 0 equals 2A plus B. So I get, so these are my system of equations. So I can solve it, you can solve it however you want, but I get that B is equal to negative 2A. So 1 equals A minus negative 2A. So 1 equals 3A. So A is equal to 1/3. So B is equal to 1/3 minus 1, so negative 2/3. So that's what I get. So 1, 0 is equal to 1/3 times 1, 2 plus negative 2/3 times minus 1, 1. Okay, and so so T of 1, 0 is going to be equal to 1/3 times T of 1, 2. So T of 1, 2 will be 2 times 1, 2. And then negative 2/3 times, when I do T of minus 1, 1, it's going to be 3 times minus 1, 1. So you compute all that, and you get the vector that E1 goes to. And then the matrix A is going to be made up of, I have that T of E1 is going to go in that first column, and then T of E2 is going to go in the second column. So you can figure out what T of E2 is, and that's going to go, so this vector here, in other words, this vector that I get here is going to go in that first column. And then I can compute T of 1, 0, 0, 1, and that's going to go in that column. So that's how you would. Okay, so did I do this one in class? I think I did this one in class. Okay. So, all right. So I want it to be perpendicular to this equation here. And so what is the normal vector of that? Well, it is 1 minus 3, 2 is the normal vector. So that would be the direction vector for the line that I want. So my line is going to be x1, x2, x3 is equal to that direction vector, 1 minus 3, 2, times some t plus the point on my line, which is minus 1, 0, 3. So I think of this as like a direction vector, and then this is like a point on the line. Okay, given the vector and parametric equations of a plane passing through, give the vector and parametric equations. Okay, so we can compute PQ equals 0 minus 1, 1, and PR equals minus 1, 0, 1. And so we get x1, x2, x3 is equal to, and you can just pick any of your points. So let's just pick 1, 1, 0 plus, and then you just want to do the span of these two vectors. So 0 minus 1, 1 times s plus minus 1, 0, 1 times t. Okay, solve the given system using Gauss-Jordan elimination. Okay, so if we try to solve it, we throw that guy into a matrix. when we row reduce that guy, we're going to end up getting an inconsistent system. So the first row reduction you do, so what we're noticing is that it looks like that this second row is going to be twice the first row, but the numbers don't match up. So when you row reduce it, when you do one more step, you're going to end up with 0, 0, 0, and then some number here. And so that means that we have an inconsistent system.